Good morning, dear students. I'm here to discuss to you Unit 5 of our syllabus, which is the thermal properties of materials. Now, as a design engineer, you must be equipped with an understanding of the thermal responses of materials, as well as full access to the thermal properties of a wide variety of materials, though these properties can be found in your ever reliable handbook. This can also be in some of your textbooks. Okay, so in this lecture, we will focus on defining what heat capacity is, specific heat, thermal expansion, and thermal conductivity, which are often critical in the practical utilization of solids. So to begin with, let's take a look at this photograph. What happens when a material is subjected to heat? Of course, the usual answer to that is it becomes hotter. Now, this photograph shows a white cube of silica fiber, so this one, which only seconds after having been removed from a hot surface can be held with the bare hands. Take a look at this man. He's actually holding that silica cube. So what transpired here? Initially, the heat transfer from the surface is relatively rapid. However, the thermal conductivity of this material is so small that heat conduction from the interior, from here, going to the exterior, is very, very small, such that the maximum temperature is approximately at 1250. But take a look, it can be held by a bare hand because, as I've said a while back, the thermal conductivity is so small that heat conduction from the interior to the exterior is so slow. Okay, so the topics for this lecture is about thermal property. When we say thermal property, it means the response of a material to the application of heat. So definitely this is response of a material to the application of heat. So as solid absorbs energy in the form of heat, its temperature rises and its dimensions increase. The energy may be transported to a cooler region of the specimen if temperature gradient exists, and ultimately the specimen may melt. So we are to deal with the different properties such as heat capacity, thermal expansion, thermal conductivity, thermal shock, and last but not least is melting. Okay, to begin with, let's define what a heat capacity is. From the definition from the book, it is the amount of heat required necessary to increase the temperature by 1 degree. So a solid material, when heated, experiences an increase in temperature, signifying that some energy has been absorbed. So heat capacity represents the quantity of heat required to produce a unit rise. So 1 degree, 1 Kelvin or 1 degree C in temperature for 1 mole of a substance. So like for example, if I have substance A, the amount of heat to raise, say the original temperature is 14.5 degrees Celsius, the amount of heat to raise the temperature to around 15.5 is what we call heat capacity, given by the equation C is Q over delta T. Okay. So as not to confuse, note the difference between a molar heat capacity and specific heat. So when we say if it is the amount of heat needed to produce 1 degree rise in temperature per mole of a substance, it is what we call as your heat capacity. It has a unit of joules per mole Kelvin or calories per mole Kelvin. However, specific heat represents the heat capacity per unit mass, or sometimes it is in small c. Some of the books uses that one. So there are two ways in which this property may be measured according to the environmental conditions accompanying the transfer of heat. One is the heat capacity while maintaining the external pressure, what we call as your CP. And the other is, of course, the heat capacity at constant specimen volume, or that is CV. I think you're familiar with this already from chem or thermodynamics. So you have learned this that Cp is always greater in magnitude than Cv, but very slight difference for most solids at room temperature and at below room temperature. So you would know that generally Cp is greater than Cv, but for most solids, Cp is almost equivalent to Cv. This only acts at room temp and below for most solids. Okay, now let's examine the relationship between the heat capacity and your heat capacity at constant pressure and heat capacity at constant volume. Note that okay, from our equation, Q is equal to NC delta T. We can get a constant pressure to be Q at constant P would be N Cp delta T. So this value is exactly the same as the change in enthalpy. So this can be also equivalent to your delta H. Now at constant volume, QV, which is also equivalent to N Cv delta T, this is exactly equal to the change in internal energy, or that's your delta U. And we know that by the molar heat capacity, that when N is equal to 1, this is for an ideal gas, you would know that if I would equate that, delta H is actually equal to delta U, review your thermodynamics, plus delta PV. Or ideal gas, that is delta U plus delta PV is R times T, right? This one, PV, that's equivalent to your RT. Therefore, if I am to equate delta H, you know that it's delta U. Sorry for that. It's delta U R times T. And by substituting, therefore, the values for here, delta H, so if I am to use delta H to be NCP delta T, that is equivalent to your delta U plus delta T R multiplied by T. Or delta U is actually NCV delta T plus R is constant, so that is R times delta T. Finally, for 1 mole of substance, you know that this could become cancel to, so NCP delta T, all the N. So this becomes Cp is equal to, so cancel din yung mga delta T, Cv plus R. Or, diba, in thermodynamics, Cp minus Cv is equal to R. So that's how we arrive at the equation, or this is the derivation of the equation for the relationship between the heat capacity at constant pressure and heat capacity at constant volume. Okay. Now, I have here list of the specific heats of some substances listed. So some of the metals would have very high Cp, ceramics, and then polymers. Okay. So take a look at this figure here. So in most solids, the principal mode of thermal energy assimilation is by the increase in vibrational energy of the atom. So these vibrations are coordinated in such a way that the traveling lattice waves, so take a look, if the normal position of the lattice is given by the orange balls here, and then the blue balls would give you the positions displaced because of vibration, you would know that these vibrations are coordinated in such a way that the traveling lattice waves are produced. So take a look at this one. So you would see wave-like positions. So note that vibrations of adjacent atoms are coupled by virtue of the atomic bonding. So the vibrational thermal energy of a material consists of a series of these elastic waves, which, as all waves, have a range of distribution and frequencies. You've learned that in chemistry or physics. So a single quantum of vibrational energy is what we call as your phonon. And this is analogous to quantum electronic radiation called the photon. Phonon is for vibrational energy, and photon is for electromagnetic radiation. Okay. So if we are to deal with thermal expansion, most solid materials expand upon heating and contract when cooled. That's the usual phenomena. So the change in length with temperature for solid material may be expressed. So if there's a change in length, that is your or final length minus the initial length all over the initial length, which is equivalent to your alpha 1 times the temperature final minus temperature initial. Or we term this as your delta L. So that's why you arrive at an equation delta L is equivalent to alpha L or delta T. Take note that alpha here is the coefficient of linear expansion, which is it's a material property that is indicative of the extent to which a material expands upon heating, and usually its unit is per Kelvin or per Celsius degree. You have to remember that. Okay. So when we talk about thermal expansion, it is actually a direct result of an increase in the separation distance of the adjacent atoms. And of course, we know that the greater thermal vibration of atoms. Say for example, at room temperature, ganito yung position ng atoms. Now, if we hit that one, there would be vibrational energy, and that you have a farther distance between two molecules at 1000 degrees Celsius. So it's the separation distance. Okay. So from an atomic perspective, this thermal expansion is reflected by an increase in the average distance between atoms. Okay. So I have here a dilatometer, which is found at the DOST Material Science Division. So it's used to measure thermal expansion. So I think I have here the coefficient of linear expansion of various materials. And for each class of materials, either metals, ceramics, or polymers, the greater the atomic bonding energy, the lower the coefficient of linear expansion. So check the values of ceramics, which has relatively strong interatomic bonding forces. So as expected, they have low coefficient of thermal expansion. The highest alpha values are found in linear and branched polymers. Okay, so because of the secondary intermolecular bonds are weak, and there is a minimum of cross-linking. So if polymers are covalently bound, expect for low alpha values. Say for example yung phenolic resins. Okay, so for metals, they have values that are intermediate between your ceramics and your polymers. So they're in between. Okay. So you have to note that weakly bonded solids, high thermal expansion is exhibited, and for strongly bonded solids, low thermal expansion. I think I have included this in some of the quizzes that I've done before. So one good example is why glassware is used in the laboratory, because ceramics and glasses have high bonding energies, therefore they have low thermal expansion, and they are excellent resistant to shock. That's why yung my parents or your mother who have Pyrex, you can use Pyrex glass straight from the oven and to the dining table. Okay. Okay, let's define what thermal conductivity is. So the basic mechanism of heat transfer by conduction, heat is by the transfer of energy of motion between adjacent molecules. And there are two mechanisms to do that. One is conduction of free electron, and what we've discussed a while back is due to atomic vibration. So the transport of thermal energy from high to low temperature regions of a material is termed your thermal conduction. So it's always from high region to low temperature region. So for solid materials, heat is transported by the free electrons and by the vibrational lattice waves, or we term that as kanina phonons. Okay, so the high thermal conductivities for relatively pure metals are due to the large number of free electrons and also the efficiency with which these electrons transport thermal energy. And by contrast, of course, ceramics and polymers are poor thermal conductors because free electron concentration are low, and that phonon conduction predominates. Okay, as you can see in this figure, I have here thermal insulators. This is your uh, ceramics, because they have poor thermal conductivity, like yung mga we term this as non-metallic ceramics, or the bricks. They lack large numbers of free electrons. Okay, let's discuss more about heat conduction. So heat conduction in fluids or solids given by this equation. This is actually the popular Fourier equation. So you will be dealing most of this when you take up heat and mass transfer, I think by next semester, and hopefully I'll still be your professor in the subject. So from this equation, your Q is a heat transfer rate, A is a cross-sectional area normal to the direction of flow. So if you say, assuming if you have here a cube, so the area perpendicular or normal to the direction of the heat flow is just this area here. Area na kukunin mo is area of this the heat flow. Okay, T is of course the temperature, X is the distance, and K is the thermal conductivity of the material being under study. Okay, so let's consider for steady state conduction. When we say steady state conduction, the heat flow is constant with time. So here, heat flow is constant with time. So how is that? So assuming, say for example, you have at time 1 p.m. the change in temperature is from 100 degrees to 40 degrees centigrade. After 1 hour, so time 2 p.m., still the change in temperature, or delta T, would still be 60 degrees. So that's a steady state heat conduction. So I'd like to derive the equation for Fourier, which is actually given by this equation, Q over A equals negative K delta T over delta X. So later when you take your hemat or your heat and mass transfer, you'll be learning more about the molecular transport equations, three equations. Your molecular transport of mass, which is deals with your diffusion, etc. Or the famous equation for the molecular transport of mass is actually your Fick's equation. I don't know if you encountered this already. Second is your molecular transport of momentum in your fluid flow. And this is your Newton's equation. And our focus for now is the molecular transport of heat, or you have your Fourier equation. Okay. Although in your heat and mass transfer, there are different types of molecular transport of heat, can either be conduction, convection, radiation, evaporation, and etc. Okay, what's the basis of these three equations? The basis of this actually is the first is you have the kinetic molecular theory. What's in the kinetic molecular theory? Chemistry 1 or chemistry 2? First is the gas is made of molecules, each of which is perfect, which has a perfect diameter of, uh, say, this one. So no attractive or repulsive forces exist between molecules. That's why, if, say, this is molecule 1, it bumps with molecule 2 since they're perfectly elastic. Even if they bump with each other, they would uh, have no attractive or repulsive forces. Okay? So the actual volume of the molecules is negligible compared to the volume between molecules. So it's the total volume is so large compared to the volume of each of the molecule. I've said a while back, all collision between molecules are perfectly elastic. So if it is perfectly elastic, they don't dent each other, or they don't. Once they bump, they could just freely distance from each other. So each molecule is in random motion at the mean speed of c bar in the random direction. So parang if I have this molecule, it can travel freely to any direction with a speed of c bar. Now each molecule moves a distance L between collisions with other molecules. So say for example, kanina ito, if this molecule collides with molecule 2, the total distance it traveled is given by L. And we term this as your mean free path. Now the time required for a molecule to travel a mean free path, traveling at a mean speed, c bar, is a mean time between collisions, or theta is equal to your L over c bar. And the number of molecules is large enough to that statistically average values of uh, properties can be used to describe all the molecules. Okay, so you've learned that from your kinetic molecular theory. The second basis is that each molecule contains properties, either concentration, so that's for your molecular transport of mass, a temperature or your molecular transport of heat, or velocity, that's your molecular transport of momentum, which can be transferred. And these are called your transferent property or your gamma. So we term gamma as a concentration of your transparent property. And the last basis for this molecular transport equation is that there must be a flux, which is a concentration of the transferent property per unit time per unit area. Okay, let's consider this following system. Assuming I have here molecules traveling from, okay, sorry for that. See, so may have molecule 1, and then these are some of the different molecules, okay? So the concentration of molecule 1 moving from this plane 1 to plane 2, so at the end, moving from plane 1 to plane 2, therefore the concentration of that, okay, let's write the concentration of molecule moving from plane 1 to plane 2 would be the transferent property or the concentration, that's gamma, over 6. Why 6? Because this molecule can travel, say in the back, let's say assuming that this is a cube, it can travel 6 different, on the 6 different planes. It can either be on top, right side, assuming that's have here, okay, top, bottom, right side, left side, and then the front and the back. So that's actually 6. So it can travel, can bump the top, it can bump the front, the right side, the left side, the bottom, and the back and front. So you have 6 faces that this molecule could actually travel. Okay? Therefore, the flux of the molecule moving from plane 1 to plane 2 would be given by gamma 1, or that's a transferent property, divided by 6 times, of course, the velocity. Okay? Or this could be gamma 1 over 6 times your c bar, or the speed. But sabi natin kanina, c bar could also be L, or theta is L over c bar. So, di ba? We have theta is L over c bar. Therefore, c bar could be L over theta. Or that would be gamma 1 over 6 times L over theta. Times, this is L over theta. So that's the flux of the molecule moving from plane 1 to plane 2. Now let's consider, going back, if it is the concentration naman, the concentration of molecule moving from plane 2 to plane 1. That could be still gamma 2 over 6. And the flux would definitely be, what's the flux? It could be your gamma 2 over 6. Take note, this is negative L over theta because it's going on the left direction, assuming that going to the right or forward moving would just be positive. Therefore, this is a negative distance. Okay? Now, if we are to consider the net change of flux from 1 to 2, so net change of flux from 1 to 2, this could be gamma 1 over 6 times L over theta plus your gamma 2 over 6. This time it's negative L over theta. Or we could say that this could be negative L over 6 theta times gamma 2 minus gamma 1. Right? So, inilabas mo lang si negative L over 6 theta, gamma 2 minus gamma 1. Or, we term this gamma 2 over gamma 1 to be the change in the transferent property over dx. Okay? Times L. If I'm to substitute negative L, therefore, all over, what is 6 theta? Theta is L over C. L over C, so this is 6 times derivative of gamma over dx times L. Or this cancels out with the L there. Finally, I would have the equation flux from 1 to 2, or assuming that's flux 1 to 2, therefore would be equivalent to negative L over 6 theta. Wrong. Sorry for that. It's not 6 theta, but it is 6 over C. Or I could bring C here. Negative LC over 6. Negative LC over 6. Derivative of your transferent property gamma over dx. And this is what we call your famous molecular transport equation. Sorry for that. Okay, so basta equation. Okay, so that's your flux is equivalent to negative LC bar. Sorry. LC bar over 6 derivative of gamma over dx. Okay. Wait. Ayusin natin. So this is actually your molecular transport equation. So the mass transport equation, the heat transport equation, and your momentum transport equation would have this as its general equation. Okay, let's proceed with your heat transport equation, or the derivation of your heat transport equation, the Fourier. Recall, flux is equivalent to negative LC bar over 6 derivative of the transferent property over dx. Okay, so this is your MLE, MTA, molecular transport equation. If it is for heat transport equation, what are the requisites? First is there should be, what's the requirement? Temperature difference should exist. Otherwise, walang heat transport. Okay, so temperature difference should exist. Second, what is our transferent property? Gamma. Transferent property gamma. There should be concentration of thermal energy. Or, what is that concentration? My Ca would therefore be rho Cp T. But temperature is your derivative of your transparent property d gamma. So if your transparent property is your Ca, derivative of your gamma, or derivative of the transparent property, would be equivalent to rho Cp dt. Take note, your rho and Cp are of course your constant. Okay, the third is define what is our flux. Flux is our heat transferred per unit area. Heat transferred, of course, is the heat transferred per unit time, and flux should be the transferent property per unit time per unit area. So we term that as your Q over A. And this Q over A would have the unit of watt per meter squared, or joules per second per meter squared. Okay, now let's plug this transferent property flux to our MTE. So flux is equivalent to, what is our flux? Your Q over A is equivalent to negative LC bar over 6 times the derivative of your transferent property, that is rho Cp dt over dx. Take note that this LC bar here, negative LC bar, is what we call as your alpha, or it is your thermal diffusivity. In the property of materials in your handbook, you can find this one, and it has a unit meter squared per second. Therefore, if that is alpha, I would have my flux Q over A is equivalent to negative alpha rho Cp dt over dx. And what is this constant here? Your alpha rho Cp is what we call thermal conductivity. Which is term K. Therefore, I would arrive at an equation that is my flux Q over A is equivalent to negative K, which is your rho Cp alpha, dt over dx. This is your Fourier equation. Okay? So you now have an understanding how the Fourier equation was derived. Okay. Wait for your hematra. I won't be discussing now your molecular transport of heat and mass and your molecular transport of momentum. I just don't know if you're taking up right now flow of fluids. I hope you've tackled the molecular transport of momentum. Okay, so I have here the table of the different conductivities of various materials. So of course, in ceramics, take note of the K. So at 100 degrees, these are the values, quite small. Of course, very high for metals. Because porosity in ceramic materials may have a dramatic influence on thermal conductivity. That is, increasing the pore volume will, under most circumstances, result in the reduction of thermal conductivity. Take note that the nearer the atoms or the molecules, the better is the conduction kasi mas maliit lang yung vibrational energy that it needed. But if you have so many pores, so assuming that this is your one atom, so may pore doon, so medyo malayo. That's why it deemed that these spaces here would make thermal conduction harder, or you need more energy. That's why you have a low thermal conductivity. So this internal pores usually contain still air, and air has a very low thermal conductivity. So kung these are spaces or air would have thermal conductivity of just around, imagine 0.02 watt per meter Kelvin. So heat transfer across these pores that contain still air is ordinarily slow and inefficient. Now, also polymers are often utilized as thermal insulators because of their, if you have, of course, a very low thermal conductivity, you're not a good conductor, therefore, you are a good insulator. So as with ceramics, their insulative properties may be further enhanced by the introduction of small pores, which are ordinarily introduced by foaming. So sa mga polymers or with ceramics, yung foaming during polymerization. That's why our most common used for drinking cups or coffee cups at your favorite fast food joints and insulating chests are foam polystyrene, or we call that as your styrofoam. It's termed styrofoam because it is being formed during polymerization. Okay, so we have here metal alloys also have lower thermal conductivities than pure metals. Why is that? Because alloying metals with impurities result in reduction in the thermal conductivity for the same reason that the electrical conductivity is also diminished. So this is due to the fact that impurity, so, diba, alloys would have impurities. So this impurity atoms, especially if it is in solid solution, act as a scattering center, so lowering the efficiency of electron motion. So one good example is shown in this figure. You have a plot of thermal conductivity versus composition for a copper zinc alloy. So if you have a copper zinc alloy, take note that the higher the zinc content, the lower is your thermal conductivity, as shown by this curve here. So if it is pure copper, so 0 zinc, you have a very high, almost 400 watt per meter Kelvin for thermal conductivity. But as you increase, take note, as you increase percentage or weight percent of zinc, you have a lower conductivity. So thermal conductivity of ceramics and polymers can be reduced by the presence of course, porosity or pores, because it contains still air. Again. Okay, let's define last one thing about thermal shock. It can be defined as a fracture or partial or complete of the material as a result of a temperature change, usually sudden cooling. So this mechanism of thermal shock involves both the thermal expansion and thermal conductivity. Okay, so thermal stresses, we define what thermal stress. Thermal stresses which are introduced in a body as a consequence of thermal changes may lead to fracture. So, or we term that as actually a thermal shock. Either fracture or undesirable plastic deformation. So the two prime sources of thermal stresses are restrained, can either be restrained thermal expansion. When you say restrained thermal expansion, you didn't give time for the material to expand slowly, or a temperature gradient established during heating and cooling. So this one is temperature gradient. It's either sudden cooling or sudden heating. So thermal shock, it is the fracture, sabi natin, of a body resulting from these thermal stresses. Okay, so rapid cooling of brittle body is more likely to inflict thermal shocks than heating. So the capacity of a material to withstand this kind of failure is we call as your thermal shock resistance. So if you are to, if the material could withstand these thermal stresses, its property would be termed as your thermal shock resistance. Okay, this is actually proportional to the fracture strength and the thermal conductivity. And this is inversely proportional to both the modulus of elasticity and coefficient of thermal expansion. That's why we have here that for thermal stress is equal to E alpha 1 initial temperature minus the final temperature, or that's your delta T. E here is what we call, diba, in your mechanical properties, this is your modulus of elasticity. Alpha is a linear coefficient of thermal expansion. And of course, TO minus TF for your delta T is a change in temperature. Okay, so upon heating, if you heat, of course, final temperature is greater than your initial. So TF is greater than TO. What happens if you have TF greater than TO? The stress is compressive, or your alpha would become, if this is larger than this one, the initial temperature, your thermal stress would be less than 0. So you have here, say for example, your rod expanded has been constrained. Now if the rod specimen is cooled, or your TF is less than your TO, of course you expect that your thermal stress would be greater than 0. Okay, if TO is greater than your TF, or initial temperature. Okay, so the stress in this equation is the same as the stress that would be required to elastically compress or elongate the specimen back to its original length after it had been allowed to freely expand or contract, with TO minus TF as your temperature change. Okay, so let's have some simple application problems on thermal properties of materials, for which after this I might be I'll be giving or uploading you some assignments. Okay, so let's have number 1. The wall of a refrigerated track body consists of a 1.6 millimeter outer steel sheet and a 9.5 millimeter plywood inner wall. Between the two materials is a 100 millimeter layer of glass wool. So the thermal conductivity of steel is 45 watt per meter Kelvin, for plywood is 0.21, and for glass wool is 0.056 watt per meter Kelvin. If the cold phase is maintained at 4 degrees and the hot phase is at 38 degrees, calculate the steady state heat flux and the temperature between the glass wool and the plywood. Okay, so we have here, you have Assuming, sabi kanina, the wall of a refrigerated truck consists of 1.6 millimeter. I have 1.6 mm steel sheet or steel wall and a 9.5 millimeter plywood. Between these two material is 100 mm glass wool. Okay, thermal conductivities are given. K in steel, 45 watt per meter Kelvin. K of your plywood is 0.21, and that of your glass wool is 0.056. Now, the cold phase is maintained at 4 degrees, assuming this is 4 degrees Celsius, and the outer or the hotter phase is at 38 degrees C. We're tasked to get Q across this body and the temperature between the glass wool and the plywood, or the temperature at this junction here. Okay? Now, let's have a basis, say, for example, because we do not know the area of the refrigerated truck. You have here, the basis is a 1 meter squared area. Know that from our equation, Q is actually negative K dt over dx, and that your, if I would have your, this is Q over A, sorry for that. Or that is your Q is actually negative Ka dt over dx. We define resistance to be dx over Ka, or if I am to take a look at this and define this as your resistance would be equivalent to delta x over Ka, or Q therefore is dt over R. Okay, the change in temperature over your resistance. Okay, now let's take a look at the resistance. Since it is, the wall is in series, therefore resistance of the steel wall plus resistance of the glass wall plus resistance of your plywood would be your total resistances. So that is resistance of the steel wall, resistance of the glass wool plus the resistance of the plywood. Okay, let's take a look. Find resistance of the plywood first. Resistance of the plywood is delta x over Ka. What's the delta x? Change, it's 9.5 millimeter, or that would be 9.5 over 1,000 to make it as a meter. K is 0.21 for the plywood, so it's 0.21 times a basis of your area of 1 meter squared. So you get that to be around 0.452. Okay, let's take a look at the resistance of the glass wool. Glass wool is 100 millimeters. So 100 over 1,000 divided by K of the glass wool, which is 0.056 times 1. So that's around 1.7857. Lastly, resistance of the steel wall, I have 1.6 millimeters. 1.6 over 1,000 millimeter per meter. times the K is 45 times the basis of 1 meter squared. You get that as your 3.56 times 10 to the negative 5. Knowing all the resistances, I could now get my Q. That is, Q is the delta T, the change in temperature from 38 to 4, which is around 34 degrees, divided by the total resistances. You add 0.0452 plus 1.78 plus 3.56. So that's around 1.831. And you could get this to be 18.57 watt per meter squared. So this would be your Q. Since it is in series, whatever is the heat transferred along the steel wall, it would just be the same with the glass wall and the plywood. So I could use your Q in getting the temperature between the two insulators, or that your Q total, therefore, which is 18.57 watt per meter squared, that is actually equivalent to the change in temperature, assuming that this is TB. So it is TB minus 4 degrees. Sorry for that. Wait. So you have here TB. What happened to my pencil? It's slow, but okay. So you have here your TB minus 4 degrees all over the resistance of your plywood, which is 0.0452, and computer for your TB, you'll get to be around 4. TB would be around 4.84 degrees Celsius. Okay, now let's proceed with another example. Say I have a spherical furnace which has an inside diameter of 2.4 meters and an outside diameter of 3.2 meters. The temperature of the inside surface of the wall is maintained at 800 degrees C, while the temperature outside is 90 degrees centigrade. The thermal conductivity of the furnace wall is given as 0.18 watt per meter degrees Celsius. We're tasked to get the rate heat transfer in kilowatt. Okay, so assuming you have, just to show you the inside and the outside diameter. Okay, the inside diameter is given as 2.4 meter, while that of the outside, assuming I have here, the outside diameter is 3.2 meters. Okay, the inside wall here is maintained at 800 degrees C, while that outside is at 90 degrees centigrade. Now we're tasked to get the rate of heat transfer, of course, from the inner going to the outer. So assuming this would be the Q that we are looking for. Okay. Then we have from our equation Q is equal to delta T over RT, or your resistance. So we could get that easily as negative 90 minus 800 all over the resistance of, what's your delta X? We need to get the delta X here. and also the area. So the area actually is 4 pi. So since it is sphere, 4 pi r1 r2, or that is 4 pi times 3.2 times 2.4. Okay, so that's roughly 24 point, I think 24.13. So if it is 24.13, I could now plug it in my equation that your RT is delta X over KA. Right? This one, it's delta X over KA. Delta X is this one. It's 3.2 minus 2.4 divided by 2. Okay? So if it is delta X is 3.2 minus 2.4 over 2, so you get your delta X to be around 0.4. So divided by 0.4 over K given ka as 0.18 times the area of 24.13. So you get easily your Q to be roughly around 7.71 kilowatt. Now, without actually knowing your Fourier equation, you could use your differential equation formula. How is that? You know for a fact that your Q is actually negative Ka dt over dx, or Q would be the integral of your dx over a from your x1 to x2, and this is negative integral from t1 to t2 of your dt times k, or k dt. Now if you know this one, you have here your 4. Q is equivalent to integral from, sorry for that, okay, Q for, so this is dx over a, you know that this is from, radius is 2.4 diameter, so that's 1.2 to 3.2, that's 1.6 in terms of radius, dr over 4 pi r1 r2 is equivalent to same t1 to t2 negative k dt, or these are constants, so I could bring that out. So I have q over 4 pi integral from 1.2 to 1.6, derivative of dr over r1 r2 is equivalent to 1 over r1 minus 1 over r2. Okay, is equivalent to negative 0.18, that's your k, and derivative of dt from t1 to t2 is t2 minus t1, or 90 minus 800 degrees C. So you have here, therefore, q over 4 pi times 1 over 1.2 minus 1 over 1.6 is equal to negative 0.18 times 90, or if I get the value of this, it would just be equivalent to 127.8. And finally, you could get Q to be 127.8 times 4 pi all over 1 over 1.2 minus 1 over 1.6. And you'll find it to be equivalent also to 7.71 kilowatt. Okay, so that ends our, oh, not yet. So I still have here some figures about melting. So this is actually a kiln or a small furnace in MSD-DOSD, wherein we have here a ceramics that is being subjected to as high as 1200 degrees Celsius. And then the material would reach a level that is already, it becomes liquid form. You can just pour it out. Okay. So thank you once again. I'll be uploading your assignment by Wednesday to be submitted on Saturday. Thank you.